So next talk is the modeling of viscous fingering. Paulo Chang will be speaking on behalf of our Professor Arne Skogge.
So I'm not Paulo Chang, evidently, but Arne has asked me just to say a quick introductory comment about the first two slides, and then I'll very gladly, as it happens, pass over to Paulo. So Arne, sorry you can't be here. I can say at Heriot Watt it's a pleasure to have Arne join us at the university. Age is no barrier to working with us, evidently. So. So that's a good thing. So Arne's GIP basically has got 6 main areas that they're working on. The first one is to do with WAG and the interactions that take place between the phases and the impact, or how you properly calculate, establish the relative permeability functions to describe this. So looking at systems where you may be injecting natural gas or CO2 as the gas phase, you've got component partitioning between the injected gas and the in situ oil, perhaps lighter end components partitioning into the gas phase, and the CO2, say, partitioning into the oil phase. You'll see a drop in the interfacial tension between the two phases as they become more similar. Actually, towards the end, you'll see an increase in the interfacial tension because by the end, you'll have just the high-end hydrocarbon components and the CO2, and you'll have lost all the lower-end hydrocarbon components from the oil phase. So how do you take account of those changing properties over time in a system? And looking at this at a fairly coarse scale, so those models on the top left there are maybe order 10 meters long, say, and looking at the fingering processes that take place there. And then the next item is looking at how do you upscale that to the reservoir scale in a robust way. And considering processes where you've got an adverse mobility ratio in that. And trying to overcome issues like phase labeling. So for example, if you have a high pressure, low temperature system, the density of the CO2 can approximate the density of the in-place oil. And so how do the rel perms distinguish between those? We mentioned earlier the need to we will still be recovering. Andrew mentioned this. We'll still be recovering oil and gas for some time to come. How do we minimize the CO2 footprint associated with that? Now, a barrel of oil produced at a 99% water cut, as is happening in some fields in the North Sea, has a much higher CO2 footprint than a barrel of oil being produced at 30% water cut, for example, because of all the extra water handling that has to take place. So I'd say enhanced oil recovery methods will be used I think increasingly as the opportunity for new licenses is restricted. There will be effort put into trying to maximize recovery from existing systems. And enhanced or like polymer flooding, for example, will probably become quite increasingly used as a mechanism of squeezing out additional oil from existing assets. Whilst trying to make them more effective, more efficient economically, but also from an emissions perspective. There are issues around multi-scale trapping of oil. So we have in our heads a picture of a relative permeability function with a certain residual oil saturation. The actual amount of oil that's left behind in the system is scale dependent, and it's dependent on the balance between viscous and capillary forces. So you may actually be able to devise an experiment where your residual oil saturation, or the remaining oil saturation, just let's be clear about language, the remaining oil saturation is a function of the interplay between these forces, which you see at a certain length scale. When you move to a larger length scale, it might be harder to see those. So how do you again, it's to do with the upscaling. How do you upscale those processes? And then looking at unstable processes, so viscous fingering processes. Traditionally, we've done a really bad job at modeling viscous fingering. So we've not been able to capture the actual saturations, the relatively high saturations that occur at the tips of the fingers. And so work has been going on trying to improve on that, trying to maximize the mobility and generate new relative permeability functions that honor the general displacement process, but capture this higher saturation that takes place at the front. And then the sixth area there is to do with, again, unstable displacement processes, but now looking at CO2 injection into an aquifer. And how do we, again, what's the balance between the various forces? Now perhaps gravity having more of an impact, taking the CO2 plume up to the top of the system, but at what point would we expect to see behavior consistent with an unstable displacement process? So 5 of these areas, the first 5 are to do with ongoing oil and gas activities, and the approach of the JIP is to look at practical applications and what field data there is, and try and develop modeling that helps understand what's happening has been observed in the field. And then the final area there is to do with CO2 storage, as I mentioned. So I'll stop there and hand over to the expert.
Professor Eric. So we don't have a lot of time, but the name of our work is Modeling of Viscous Stability in Compositional Gas and WAG Injections. This is a repeat work from, I think, 3 weeks ago, so some of you may have already seen those that were in the EOR conference in the same hotel, actually. And so what was our objective? So we were trying to model 3 things at the same time. So WAG hysteresis effects coupled with unstable flow, aka viscous fingers. And we also try to see the impact of varying degrees of miscibility in these simulations. And so, we use the WAG hysteresis model developed by Larsen Skog, and then we applied the methodology by Sorby et al. To model the unstable flow, and then we come out with different fluids with similar properties but different miscibilities. And the first part of the methodology, so related to unstable flow, and this is a very brief summary of the methodology applied by Sorby et al. The first 2 steps are actually to derive the rel perm for the gas liquid curves. And the main idea here is to have to modify the rel perm as to obtain high saturation shock front, and also a high mobility in that shock front. So the idea is, by having a high saturation shock front, you have sharp fingers and also maximize its mobility. And so we can match some of the data obtained by Skog et al. Some years earlier. And the second part consists in modeling a porous media that is compatible with fingers. So the idea is you have a random correlated permeability field, and you have fine enough grids so that you can see the fingers on the media. And for our WAG model, these are the main parameters: the dampening exponent, the length constant, and the constant that couples the residual saturation, the 3-phase Stone 1 model with the trapped gas saturation given by SGR. This is our WAG injection scheme. So we inject 5 slugs of gas and water. So each slug comprises of 1 per volume in reservoir conditions. And so we start with gas, then we come with water, and then we repeat this 4 more times to give 1 per volume total. And this is just so we can visualize the hysteresis effects in the reservoir. On the right, you see sorry, I can point it, but you see in black the rel perm for the gas, and in blue the water, and in red the saturation of the gas. So you can see the sequence of injection in there, and also the effects of the reduction of the rel perm. And on the left, you can also see the cycles. You start injecting gas, and then you reduce the gas saturation by injecting water, and you trap a bit of gas, and then by redoing the process, you increase the gas being trapped in there. And for the water rel perm, these are the 2 curves that we use. First, the 2-phase rel perm, which is the classical water oil relative permeability, and then the 3-phase, when you reduce the oil to its residual saturation and replace it by gas. And so the final water relative permeability will be an interpolation between these 2 curves. And finally, for fluid models, we have a fluid model with 5 pseudo-components. And the CO2 makes up the gas, so we're injecting 100% CO2. And the other 4 pseudo-components, hydrocarbon components, make the oil in place in the model. This table shows the properties for the immiscible case, but they're almost the same for the other 4 models, which would be also the near miscible A and B, and the miscible case. And the idea here is that by having very similar parameters for all the fluids, you have the same properties for at least the single-phase gas and oil. The only difference between them, at least for reservoir condition, sorry, and the only difference between them would be the miscibility of the CO2 oil system, and we do that by altering the binary coefficients of those models. And so to do that, the idea is very simple. If you have a positive value for binary coefficient between the CO2 and the hydrocarbon, you're accounting for an increased repulsion between these 2 components. And so in effect, you're raising the minimum miscibility pressure or reducing the miscibility. If you use a negative value, you have the opposite effect. And so, for example, these are a table that shows you all the binary coefficients that are not 0 for all the 4 fluid models. And for the immiscible, I had to use a very high value between the CO2 and the other oil components. And we also had to use a very negative value for this one so that the methane doesn't go into the gas phase when you have a phase splitting between these 2. And for the near miscible, we have more conventional values. In the miscible case, CO2, in many cases, is already miscible in the system, but for our pressure and temperature conditions, we had to increase a bit its attraction with the other components. And here you can see the px graph, so you can have a feel of how much CO2 you need to inject before the phase is split in your system. So some of the results. Here I'm showing you a map of the gas saturation for all 4 fluids, the immiscible up onto the miscible case. And you can see in the immiscible case the sharp fingers, as we wanted to see. And of course, when you have when you have some miscibility in the system, you delay a bit the velocity of the gas, and you also make the fingers a bit sharper. And here I show you the CO2 normalized concentration, which is the total concentration of CO2 times everything not water in our model, just so we can follow the CO2. And it's interesting to compare, because in the miscible case, most of the CO2 is on the oil phase, but it condenses on the oil phase, so there is not a lot of gas in the system, and that will have an effect later on. I'll show you. So yeah. Because of our choice for the gas-liquid relative permeability, we can actually see sharp fingers on the immiscible case. And in the near miscible case, these fingers are even sharper. But that's because, in this case, mass effects are dominating the flow on the shock front. So because of mass changes, a lot of the CO2 is actually being condensed on the oil before the phase split. And that will create an even higher saturation for the shock front on those scenarios. And in here, I'm showing you some oil recoveries in our simulations for all 4 fluids and for 4 different scenarios. So in red, you have the gas flood, so it's 1 per volume of just CO2. And then in blue, you have the water flood. And you can see the colors in there. So the dotted blue line is the water flood, and the dashed dot purple line is what I'm calling WAG, no hysteresis. We're injecting water and gas, but the hysteresis model is switched off. And finally, the solid green line is the WAG results. So the first thing to point out in here is that because of our water flow is stable, you have a pretty good aerial sweep in our model. So, and that's the opposite of what's happening in the gas. So they are both complementary, and you can see that in all cases the WAG injection with and without hysteresis is not somewhere between the gas and the water recovery. It's actually better than all of those, even when the gas actually has a higher recovery than in the model. And as in this picture just shows it, so you have a 0.4 per volumes injection. You can see that the water will sweep, or at least will contact all of the cells in our model, and that's because even though it's a very heterogeneous model, there's no coarsening trains on it, and so in a way it's homogeneously heterogeneous, and with a stable flow you have a very high aerial sweep efficiency. And of course, the largest impact of the WAG simulations occur for the immiscible, where you have the worst initial recovery, and also you have more gas in the system in the immiscible case, which is mainly how the hysteresis model will activate. But for the near miscible cases, also you have a significant impact on recovery. So, and from what you could see, the WAG model is working relatively fine for these near miscible models. But for the miscible case, since most of the CO2 is on the oil phase, you don't see a lot of difference between the WAG with no hysteresis and the one with hysteresis on. And that's because with no gas in the system, you won't have an interference between gas and water, and the model won't capture, nor will it trap the CO2, and so you see no impact in our simulations, of course. It doesn't mean that won't happen in a real scenario. And in here I show you what happens to the recovery for each individual component. So you can see, especially for the near miscible A, you see a large spread between the recovery of the lighter components and the recovery of the heavy components, and that's something that most everyone would expect, really, because the CO2 will strip the lighter components of the oil, leave the heavier ones behind. That you can see that also happens on a smaller scale for the immiscible, although the system is supposed to be very immiscible. So even so, some of the methane does go to the gas phase, and that because you're passing a lot of CO2 in the system on the fingers, it will tend to be more stripped than the rest. And in here, what happens if you then inject water? Well, water will displace the components, the oil components equally, so you tend to reduce the spread. But if you then switch on the hysteresis effects, it will help you to mobilize the heavy oil components, mainly by reducing the residual saturation in the system. So when you trap the CO2, you have that equation that I showed you on the first slides. You reduce, at least in our model, you reduce the residual saturation, and this will help you. Also, you reduce the relative permeability, and so this will help you to mobilize the heavy oil components. And this, as you can see, also this in this map here. So in the first, So in the first slide, you see well, for all three cases in here, I'm showing you what I'm calling hydrocarbon saturation, which is everything not water times everything not CO2. So just to give you an idea of where the remaining oil is on the system, and this is after we inject 1 per volume. First gas, and see there's a lot of oil left behind on the bottom of the model, and then after inject water, you remove a lot of that oil. But still, I'm not sure if it's, the picture is not showing that clearly here, but there's a lot of mostly of the blue in the middle picture is actually a lighter blue, and that becomes a darker blue on the picture on the bottom. And those lighter blues are the heavy oil with low saturation that are also immiscible, because they are the heavy components left behind by the CO2. And when you apply the hysteresis in the model, you recover a lot of those oil left behind. You can also see that on this histogram in here. So if you compare the blue histogram with that's WAG without hysteresis and the green one, you see that you reduce a lot of the residual oil in there. I don't have a lot of time, so I'll try to rush. We also saw the effects of viscous crossflow on recovery. We know that there's some earlier work that shows that this happens, but we just try and see how it's affecting our model. So first, just to understand it better, we did a very simple example. So this is a constant permeability, and there's a high permeability strip right in the middle of the model. So what will happen in a WAG simulation? So the first picture is the end of the gas lug, so the first gas lug, and you are just circulating gas. But then when you start the water injection, you can see right in the middle that there is an increase in the oil saturation. That's our viscous crossflow, and with further water injection, you're just displacing and producing this extra oil in the finger. And there's a lot of curves in here, but this is just so we can maybe try to understand better what's happening in there. So the blue line is the water saturation, the green is the oil, the red is the gas, and the black line is the difference in pressure between the edge of the finger and the center, and the purple lines are the mobility in the center on the edge of the finger. And so you can see on the first picture that, you can see on this first picture that the black line is almost zero throughout the fingers. It means it's stable. There's no fluid exchange between the outside and the inside of the finger. But when you inject water, you see that there is an increase in this gradient right on the interface between the water bank and the oil. And that's where our oil is entering the finger. That's because the mobility of the water is much lower than the mobility of the gas inside the finger, and also even lower than the mobility outside of the finger. And this will create a pressure differential, and then the oil will invade and start displacing the gas. And in our simulations, do we see this? Yes, also. So this is also for the near miscible case. Also, the first picture shows you the end of the first gas injection, and then when you inject water, you can see on the last picture, I'm plotting what I call the delta oil saturation between the second and the first pictures, and you can see an increase in the oil saturation there, showing that yes, it's a lot of viscous crossflow in our simulations. And finally, we also realized that a lot of the trapping, the gas trapping, is actually being done by the oil phase, at least in the start of the simulation. So first, this happens because some of the gas in the fingers, because of buoyancy forces, they are migrating to the top, and the oil is coming down. And when you have this oil invasion, our model will capture this and trap some of the gas, even before you have any water injection. But after you start injecting water, then you have also the crossflow effects, and this will trap a lot of gas throughout the fingers, even where the water is not reaching it. So that raises an interesting question. Should we consider also interfacial tension effects on phase trapping? And that may be very important, for example, in a near miscible simulation. So finally, our conclusions. WAG had the largest impact for the immiscible case. The WAG hysteresis model seems to work satisfactorily for near miscible scenarios. And if our model is right, WAG, besides increasing aerial sweeping efficiency, will also help us with recovering the heavier oil components in a near miscible case, for example. And our miscible case, because of what may be some labeling issues, we don't see a lot of effects by using the hysteresis model. That can happen, of course, if our model would identify the system, the CO2 oil system, as gas for lower saturation or lower concentrations of CO2, then we could see an effect. Or maybe we need to upgrade the model to consider composition instead of just phase saturations. Sorry. And cross flow in the fingers do accelerate oil production in WAG, and because of its effects, a lot of the gas trapping is actually being done by the oil phase, and so it would be interesting to identify interfacial tension effects on phase trapping. That's it, and these are our sponsors. Thank you very much.
Thank you, Paulo, for taking over the talk. It's excellent. Any questions from the audience here? Let me ask the first question then. How would you upscale your lab experimentation, which is outstanding in terms of the fingering and whatnot, to a larger field type of model? Do you use pseudoperms and hysteresis? How do you kind of modify that to a field scale history match and forecast?
Yeah, that's a good question actually. For the fingering, one idea is well, not my idea, but from a colleague, Victor Hughes. His idea actually was to make the oil or the CO2 oil system to be less miscible than it really is, so that you can see a gas phase in the system, even though if you would just go with your fluid model, maybe in some cases you have like a full miscibility. But because you have fingers and you have these viscous finger flows in the system, you do have like free gas in the system. So his idea was to, when upscaling, to reduce the miscibility artificially of the system and make it, so maybe you could capture this extra gas phase in the system, something like that. Yeah.
So has that been attempted? I understand that Dr. Skoge's got a big consortium of industry participants behind you with their names. Have they actually provided field data to attempt a history match with that idea?
It's complicated to get our history match, but we did do that at some fields at Petrobras where I worked. And it's very hard to say that we are really matching, we're doing the right thing, but we do need to reduce the miscibility in there in some cases so we can match some gas history data, gas breakthrough history data.
Okay. Any further questions? Okay, if not, once again, thank you